So I'm excited to have Eunsol here. I've known Eunsol since 2011 when she was an undergrad at Cornell, and she was working with me and my advisor William Lee. And then she went off to University of Washington, and clearly she's doing great. And she has done excellent work in question answering and information extraction. Today she's going to tell us about entities, and let's welcome Eunsol again.
Thanks for kind introduction. My name is Eunsol from University of Washington, and I am very excited to talk about my research on learning to understand entities in text. Okay. So as an NLP researcher, we have a long-term goal of building an intelligent agent which can read and understand text and help us in our day-to-day lives. So easiest example is a Google Home or Alexa, which is already with us, which understands simple instructions such as setting a timer or tell us about the weather of today. But this is one simple example, but we want to actually go further and build machines to understand the streams of text and give us insights and analysis. For example, like reading the news stream, it must be able to automatically understand how's the public's opinion towards particular politicians or events. So this is like going more overarching, like a longer-term goal. And at the end, we actually want the physical robots which can read and understand all sorts of text, including like recipes and WikiHow, and actually do stuff for us. So to be able to do all these things, the intelligent agent must be able to read and understand text. And what I mean by understanding text is really about understanding the entities inside it then. So say that you are reading a lengthy novel about like multiple characters in it. Like after reading the novel, you should be able to understand the characteristics about each characters as well as the relationship between them. And when you're reading news articles, you should be able to understand who are the key agents in the news articles and how they interact with each other, what are the main events that's happening. And when you're reading recipes, you should be able to understand the entities in it, like tomatoes or avocados, and like actually understand how they change when you like put heat or like water in it, and how they change when they mix them. So these kind of understanding the actual agent inside it are really important. And not surprisingly, the text can convey a lot of information about these entities. So here's an example, two example sentences. A previously unreleased novel by Lord of the Rings author Tolkien is set to be published. The writing of this book was partially prompted by his harrowing experiences in World War I. So after reading these sentences, you learn about four main entities. The novel that's unreleased, and Lord of the Rings, and then Tolkien, as well as World War I. And after reading this sentence, you actually learn things about them. So because it's experience in World War I, you know that World War I is kind of an event. Tolkien must be a person, Lord of the Rings, and then this unreleased novel is an object. Not only that, you can also learn about the relationship between entities. Tolkien wrote these two books, and then he witnessed World War I. So these are like some kind of information that you can learn by reading text. And there has been a very rich literature trying to focus on entities in NLP. So understanding the types that they belong to is called entity typing. And understanding the relationship between them is called relation extraction. And those are very important applications. And I'm going to talk a little bit about like this kind of structured representation. But later in the talk, I'm going to talk not just about this kind of graphs, but about just looking at the raw text as well. So after you build this kind of representation, you could put that into a giant knowledge bases, which can contain a lot of facts. And then machines can have this understanding of entities, which can help you better. Okay. So based on this kind of existing formula, like what kind of questions that the machines can answer. So here are a few examples. Based on that graph, if you ask like who wrote the Lord of the Rings, machines can easily answer J.R.R. Tolkien, as you can try with your Google Home or Alexa. And based on that graph, you could also do some kind of reasoning about counting as well. So if you ask how many books did J.R.R. Tolkien write, it should be able to answer that at least 2 or some number. Okay. So this is what we have been able to do. And now I'm going to talk about some things that the current NLP was not able to address that I was trying to work towards throughout my PhD. So one missing piece that is about learning implicit knowledge that's hidden between the text. So for example, after reading those two sentences, if someone asks you, how did J.L. Tolkien feel about World War I? He was inspired by his harrowing experience to even write a book, so you should be able to answer that he disapproves of it strongly. And there are other kinds of implicit information. What is Lord of the Ring? The Lord of the Ring and then Tolkien was related by author, so you can like kind of guess the type of a book. So this kind of implicit tacit information about entities are rich in language, and we want machines to be able to understand this kind of unspoken informations as well. Secondly, second part of the talk, I'm going to talk about interactive querying. So you want the machines to be able to answer not just each single questions, but a sequence of questions that you pose. So for example, you ask who wrote Lord of the Rings, it says J.L. Tolkien. You want to ask a follow-up question to learn more about him. Did he write any other books? It should be able to answer, yes, partially prompted by his harrowing experiences World War I. So this is kind of like two themes that I'm going to talk about today, like how can we infer this kind of implicit informations, and how can we interact with the machines to gather more informations. So both of the work has kind of similar theme of like trying to expand the horizons of existing NLP to cover more richer semantics and understand, make the machines to understand better the details about the text. Okay. So before diving into like a cool research project that I have done, I want to give a little bit overview about like how I view NLP as a field. So analysis that I'm making here is the arms race between the data and the model. I put data as a mouse who's like trying to run away from the model. And then the model is a cat who's like trying to catch the mouse. And both has been really, really important in the progress of NLP. Like finding the data that captures the phenomena that we want to capture, like a machine translation, where we have a pairs of sentences that from different languages that same meaning, or like a sentiment data set, those things basically, and as well as like a tree bank and like prop bank, all these things, some of which Martha and like people here are involved in, was really important. And also on the other side, building the models which can actually capture this phenomena, doing it more accurately, more efficiently, and in a more interpretable fashion is also really important. There has been some crucial ideas as well. And this is not just NLP, and I think like it kind of goes along in like a vision and other like hereditary field as well. And throughout my research, I have been working on both modeling side and then the building the data side. So throughout my talk, you are going to see some cats jumping around and mouse jumping around throughout the talk. Okay. So I'm going to dive into the first part where I'm talking about inferring the implicit informations. And particularly, I'm going to focus on the relations between the entities, sentiment relations. So say that there is a pair of entity, Russia and Belarus. You want to see whether it's a positive or negative or neutral. It's a simplification, but sometimes it's useful to make this simplification to actually build models to be able to do it. So this task is called targeted sentiment inference. It has been studied in NLP in prior work as well in a setting that's like focusing a single sentence. So you're looking at a single sentence and a single pair of entities and trying to find how they feel about each other. So in this work, we are kind of expanding this work, which was doing just looking at a single sentence and a single pair, to look at the document level and trying to understand this complex web of like interactions and the feelings between a set of entities. Okay. So this is obviously a much harder problem because now you have to be able to do the inference across different sets of entities. So say that like there's an article about Taylor Swift and Ellie Goulding, and like Taylor Swift said something negative about Katy Perry, not because she has something bad thing about her, but just because she's a really good friend with Ellie Goulding and they have relations. So machines now have to be able to do these kind of reasonings because there is a tie of this kind of relations that's like a bond between different entities. And not just like kind of relational, but sometimes it's more factual relations. Like when the Moscow and Russia is like repeated in the same article, they usually have the same opinion because they are representing the same bigger set, which is Russia as an entity. Okay. So now the machine has to be able to do this kind of inference, taking account this factual information as well as entity-entity sentiment dynamics. The second thing that our model have to do is do the document level understanding. So look at this document. It's about Russia heat smoke trigger health problems. We never care to work with a future perspective in mind. Alexei of the federal agency said it's a big systematic mistake. It's actually really hard for traditional NLP system to find this relationship between them because they don't even appear in the same sentence. But the sentiment is pretty obvious here that he's negative toward Russia. So now the model has to be able to do document level understanding. And for this particularly challenging task, we are proposing a document level model. So the model now has two parts. The first is a pairwise model, which is basically following the prior work, trying to find the relationship between a pair of entities, whether they are positive or negative or neutral toward each other. You train a classifier with some features. And then there are second part of the objective, which is trying to incorporate this dynamics between entities to give more coherent sentiment predictions. So I'm going to talk more about these global constraints in the upcoming few slides. So we're going to use integer linear programming to enforce this kind of like constraints about like how coherent the entity-entity sentiment should be. And IRP, just for a little background, is kind of optimization task where there are binary variables and you could kind of put constraints between different binary variables. So for example, in semantic role labeling, you could kind of put stuff like for each verb, there should be one main argument, not two. And here we are looking into the dynamics between entities with this kind of constraints that we are going to put globally. So the model as an IRP has a binary decision variables. There are like three types of decision variable. One is whether they are positive toward each other. And then the other is whether they are negative toward each other. And the last one is they have any factual ties. And then the last thing, the factual tie, is going to be just we heuristically extract with some rule-based methods, finding out that Gryzlov is, for example, president of Belarus and so forth. And then the model is actually trying to make a decision about whether they are positive or negative toward each other. And the objective, that's the trained pairwise classifier, we're going to basically drive the decisions. But on top of that, there will be a global constraints which are trying to incorporate the intuitions from social sciences. So one intuition that we are trying to incorporate is the principle called homophily, that entities in the same faction shares an opinion. So say that Gryzlov is a president of Belarus, they are connected with this factual tie, and then he said something some negative statements toward Russia and some positive statements of Georgia, then you can kind of guess what the Belarus's opinion towards Russia and Georgia, right? It's going to be more likely to be aligned with what Gryzlov is thinking. So this is encoded as a binary variables, and then the model is trying to satisfy this binary variables, and how much you care about this particular objective is decided by the hyperparameter alpha, which you can tune on the development set. Okay. So this is like one soft constraint that the model is trying to get to. The second constraint that we are trying to put into the model was another theory from social science called social balance theory. So for a graph of relations, there are some graph status that's more stable and balanced, and some are less so. So for example, if Belarus is negative toward Russia, and Russia says something negative about this representative named Mihai, then it's more likely that he's positive toward Belarus because enemy of enemy tends to be a friend. Okay, so this is similarly encoded. And then now after we have built the model, we are trying to do the evaluation. So we basically, the model outputs this predicted graph of relations between entities. And there is a human annotated graph. We actually collected a smaller scale data for this. And then now we are basically comparing whether the positive edges are correctly captured and whether the negative edges are also correctly captured. The results are for positive and negative edges. So F score is how many of those edges are recovered. And randomly assigning edges based on the distribution, of course, doesn't do as well. The sentence level model doesn't do very much. And then the document level model, which is the yellow bar, does significantly better than just like aggregating the sentence level informations. And when you are actually putting into this global constraint that's coming from social sciences, the both performances for both positive and negative labels were improving. So in this part of the talk, I talk about this like a document level sentiment inference task where we could actually build models which can like reason with some commonsensical knowledge about entity-entity relations. And also I thought that interesting part, like looking into how factual relationship can affect the sentiment relationship was also really new in this work. Okay. So I talked about this, and I talked about this a lot of inference, and I'm going to talk a little bit about something that I found a little bit troubling when I was actually looking at the inference that the model was making. So say Martha is positive towards Chen Hao is positive towards Jim, then it's like, it's a collegial department, people like each other, so it's pretty okay to infer that Jim is also positive toward Martha, right? But then you look at this other example where Chen Hao is liking GPU. Like if you say that like, GPU like Martha, it's like not quite right. So the inference should now really, to be correct, should understand the entities a lot better. So in the second part, I'm going to talk about how can we help the models to understand the entities themselves better in isolation. So here we are going to propose a new task called ultrafine entity typing, where given a sentence and a noun phrase inside it, predict a set of categories that such noun phrase belongs. So it's always easier with the example. So here's an example. We have very exciting prospects for far more impressive advances in the treatment of colon cancer during the years immediately ahead. Okay, so now it's time for you guys to participate. What is the we here? Any guess?
People.
Okay.
Researchers.
Uh-huh.
Doctors, society.
Right. So as humans, we could make a pretty like a finer grained inferences about what this we is going to be like, right? It could be organization, people, scientists, researcher. Here are some like, annotations that could be correct here. And this is a task that we are interested in. Like NLP jargon, it's called entity, and these things are called types. Okay. This is not a new problem in NLP. We have been doing this problem actually for about 20 years. So in 1995, people come with this task of named entity recognition, where we read the sentence, identify the entity mentions, and basically classifying them into 4 possible buckets, like person, location, organization, and everything else, basically. And then because people found this like 4 types are a little bit too coarse, so about 2012, people were actually coming up with this like a finer grained entity types, where they are now covering more informative types, such as a doctor, organization, doctor, like hospital, and like athletes, and so forth. But still, in this example, both Bill and John will be annotated just as a person, because nothing is in this like 100 categories. So actually, when I was actually looking into this data, there are like some problems with the evaluation data set. So actually, when you look into the actual label distributions, many concepts like doesn't have very informative types among this 100 set. Like more than half of them was just annotated as other on one of the data set. And here are some examples. They couldn't find a good concept. Like, but you can kind of imagine the Paris Agreement, security mortgages, and oil. It's kind of hard to put them into some bucket. So the key idea of this work was like allow any commonly occurring nouns as a type, not limiting to this like 100 hand-picked ontology. So here's actually the distribution of this previous data set, which both of them actually have about 100 types in the ontology. But actually, you're looking into the label distribution. If you can cover about 5 of them, you cover like 80–90% of them. So if you train machine learning model on this kind of distribution, it will never learn to predict the 100 types that you want. So this is a new data set that we collected. I'm going to talk a little bit about the collection methods, and you could see that like this data set is like a much more diverse, really capturing the fine-grained labels about entities. So we call it ultra-fine entity typing, and now you can label Bill as a criminal and John as a victim. So here the space of answer is like 10,000 most commonly occurring nouns in Wikipedia and news articles. So you might wonder, like, why do we care about entities? I was trying to motivate a little bit with sentiment inference, but if you want to do question answering as well, knowing the types of entities here can also help solving QA. And there are some examples in someone else's work where they're trying to use these types to improve the end task that you care about. Okay. So now I'm going to give you one other example that's actually in our data set. The Inti Romney was the most important of 4 ceremonies celebrated in Cusco. And the label was pretty fine-grained. It's an event. It's a festival, ritual, custom, ceremony, party, and celebration. And how we collected this data, we went to crowdsourcing Mechanical Turk and basically asked the worker to give one general type for the entity, such as an event. and 2 finer grain types such as a festival and ceremony. And then we gave the exact same example to multiple people, actually 5 of them. And after this collection, we did some validation phase, and then we end up with a very, very fine-grained labels. Here are some things that I wanted to highlight, like employment, religious leader, language, computer games. There were like a lot of interesting concepts in there. So overall, it was about 2,000 types over 6,000 examples that we collected. So now we come with this like a really rich label space, but we only have 6,000 examples, and now the model is like having a hard time trying to solve this data. So I'm going to talk a little bit about what kind of training data that we can use to actually do this kind of detailed inference. So one thing is you're using the crowdsourced data. You know, we can collect with like Mechanical Turk, but it's kind of costly and hard to do large scale. So we are going to turn aside and looking into this kind of weekly supervised training data which you can get for free, but while it's somewhat noisy. So the first weekly supervision data is actually coming from the literature. We improved it with by making it a little bit more larger scale, but the main idea is like pretty cool, so I want to talk briefly about it. So the supervision here is like they are using the pre-populated databases. And say in this example, Arnold Schwarzenegger is giving a speech at City Hall on Veterans Day. And you just find this Arnold Schwarzenegger in a database with entity linking. And in the database, they already know who he is. He's a person, politician, athlete, businessman, artist, actor, and author. And from this, you are basically getting the free supervision. Like someone who's giving a speech at a City Hall on Veterans Day is more likely to be a person, politician, and then so forth and so forth. And this is like pretty sweet, but there's some problem here. So when you're trying to generalize from this example to this new example where the entities swap to be a Barack Obama, and now the model might predict that Barack Obama is an athlete because it learned from the previous example that athlete fits into this context. And so basically the problem is like not every type's coming from the sources are context sensitive, and sometimes it makes it like a noisy and harder to generalize to new examples. So in the next slide, I'm going to talk about new sources of supervision that we introduced that doesn't suffer from this context-insensitive problems. We call it headword from noun phrases. So look at this example. Controversial Judge James Pickles sentences Tracy Scott to 6 months in prison. Like, we want to know what is this entity, but the answer is actually there. Like, the fine-grained type here who's like sentences someone to 6 months in prison is a judge, and it's just there. So we're trying to basically use this free supervision from this headword, which provides a very, very fine-grained types, which is almost always sensitive to the context. So now we have like these 3 kinds of different buckets, and then we are trying to train a model which can use all these 3 kinds of buckets. So this is a pretty standard model architecture. We have basically embed the sentence with word embeddings and then do some recurrent neural network. And then on the top, you train basically sigmoid for each of the labels, whether this is, should be turned on or off. And then we improved the architecture a little bit, and then the loss is also modified because we are combining different sources of supervision a little bit. And first, we want to kind of try how well this model was doing. So we tried on this existing benchmark data, which covered about 100 types. And then looking into the F scores between the human annotation and then the model predictions. And then the prior work was doing pretty well because it's kind of coarse-grained. It was getting about 63. And then when you actually added the new supervision sources that we found, the same model was doing substantially better because of the new data. And then when you actually swap with our model, it was getting even better. So now we see that it was like doing reasonably well on this like a smaller label space, and what we really wanted to see is like how well it does in this like a much richer label spaces. And as you could imagine, the F1 score dropped significantly. It was getting about only 30%. But when you're actually looking into the examples, it was kind of like encouraging that sometimes the model was able to predict a really fine-grained types. So in this example, for him, the economic outcome is not by chance, but the result of action depends on indispensable reforms which were much discussed but not yet implemented. Human annotated this as a person, politician, economist, leader, official, business person, and businessman. And then the model was able to correctly predict the first 4, but missed the other 3. So it was actually not getting a very high score because the recall was low. But it was kind of encouraging, but there was still a lot of room for improvements about how to get F-score higher and also how to evaluate, because sometimes the annotation is not always super consistent. Yeah. So in this part of the talk, I talk about how can we improve the entity typing by improving the coverage of labels, as well as bringing a better data and a better model to solve the task. So the first two parts combined is covering this kind of implicit information that can be inferred from the text, like how they feel about each other and like what kind of categories that each of the entities belongs to. So this is kind of closely related to which prior work. Basically, we are making these edges more informative by making a finer grained prediction that it's a book, a novel, or author, and as well as like adding new edges about the subjective feelings about the entities toward each other. Okay, so now I'm going to move on to the second part, where I'm going to talk about slightly different thing, about like doing the question answering in an interactive fashion. And here we are going to switch gears a little bit and look into different types of question answers. So here we are asking a question for, was U2's new album successful? And if you're asking this question to your friend, for example, if that person just say yes, like I would be annoyed. Like I want more detailed answers about like why does he think that this new album was successful, right? So it could be either the air show in Las Vegas was attended by over 150,000 people, or the tour concluded with like a gross revenue of like a large sum of money, or the album broke a sales record in the United States. Any of them is fine, but you want this kind of more finer grained text that comes as an answer. And there is kind of a framework in NLP that the test that we are using that could do this, which is called the span-based reading comprehension. Here, we are giving a question and a document to a machine, and machine finds the answer by selecting a span from the original document. So it's a copy and pasting from the original document. Okay. So how this new form task has come into fashion, it happened in 2016, where Stanford people crowdsourced a very large scale of this data, which pairs question, document, and a span of answer. And this kind of limitation of limiting answer to be the original span makes it much more easier to collect a large-scale data. And another really important thing is that it made the evaluation much easier. So now the space of answer is like restricted to the original document. So the answer of the humans and the answer of the machine can be compared and can compute the precision and recall and F1 of the word level overlap between those two. So here, the two habitat preservation, all tokens were in the human answer, so precision is 100, but somewhere means the recall is lower, and then F1 is so forth. Okay. And after this has been introduced, there has been like a tremendous progress in our field about pushing these numbers up, basically. Most of the progress was like better neural network architectures, but you see that like now the models are doing as well as a human on this particular framework. But one thing that I was not like so happy was that all questions are independent, where humans don't interact in that fashion. Like when you are trying to learn more about something, we just keep asking questions, like inquisitive toddler who keeps asking you questions until you get tired, basically. So because there was no data, which has this kind of QA pair, so the thing that we went and do is like collect a large-scale data. So again, we went to Mechanical Turk and paired up two workers, one as a student and the other as a teacher. And the job of student is pretty simple. It has the name of entity and then a brief introduction about them, and then like trying to learn as much about this particular entity. And teacher's job is it has given a document and the entity name and trying to answer the student's question by choosing a span or saying no answer if the answer is not in the original document. And after we collect this data, what we actually want is replacing the teacher with the model. So that you ask a question and they give you the answer that you want. Okay. Now I'm going to give you one example dialogue in our data set. So this is about Daffy Duck, the characters, and how they come to life, basically. So students, given this topic, ask the question, what is the origin of Daffy Duck? Teacher answers, like, first appeared in Porky's.com. The follow-up question is, what's he like in that episode? Answers assertive, unconstrained, and combative. Was it a star? Barely more than an unnamed star in this episode. And then who was the star? And then because this is about the epiduct's origin, the answer was not there, and then it says they cannot answer, so conversation goes like this. So it's kind of limited and a little bit clunky, but basically people was able to go through this dialogue, and we collected about 14,000 of those, and each of the dialogue have about 7 question-answer pairs. Now I'm gonna show some more examples about questions in there, and what kind of challenges the model should be able to do to solve this task. So here are some examples. Did she win an award? What happened afterwards? How popular did he become? So to be able to answer these questions, the model must know who is she or he that's referred to. So what kind of entity they are talking about. Another important thing is that now the model have to understand the dialogue history as well. Like which happened afterwards. To be able to answer this question, the model should know what was the answer to the previous question. So I have introduced the problem. Now I'm going to move on to you're curious how well the current machine learning methods can do on this particular benchmark. So you start easy, random sentence, just pick randomly, and then the F1 score is not as good as you can easily imagine. And we set an upper bound by asking the same question to suit different set of people and how much they agree with each other. And you see that the numbers are on the 80s, so they are pretty consistent with selecting the span from the original documents. And then now you have to build a real baseline. And because sometimes we are lazy, we're just trying to take the best model that's existing out there for the single term question answering, because it's a pretty similar problem. And you just take this model and then see how well it does. And luckily, it's doing reasonably well, but not as well as humans. So as a data set maker, this is kind of a sweet spot. The model is doing reasonably, but not as well as the humans. So there is a rich room for model maker to build a better model to catch the mice. Okay, but I also want to make a better model. So as a follow-up project, we actually worked on building a better model for this particular data. So this challenge that we found that the current model was not doing is incorporating the dialogue history, like what has been talked about. And this information is really crucial to answer the existing questions. So for example, in this part, the second question, so why did people feel that way? Without any context, asking the model to be giving the answer is kind of really hard. But if we knew about the first question, was Mickey Mouse known for being intelligent? The answer was no, he was publicly known as a character with a lack of culture. Then now it's the second question makes much more sense. That's what come on, man. Okay. So how are we going to do that? The quick and easy solution that we came up with is just concatenate the prior questions to the current question and mark the documents about the locations of previous answers. So basically, you modify this input space, so now model knows all about the previous dialogue history. And would this help? Luckily, it was helping quite a bit. So this is a graph that shows the performance of the model and also humans. So 0 is the start of the dialogue, and it goes until 12. And the humans agree with each other throughout the dialogue consistently. And then the baseline model, which doesn't have this input concatenation, which is a green line, gets worse and worse as the conversation goes on. And this is kind of goes along with your experience with Alexa or Google Home. You ask one question, and you ask a follow-up question, it gets worse and worse and worse. And even after concatenation, it was still there were some degradations. So in this project, what we are trying to do is how can we model the conversation history better? And what model knew by concatenation was the prior question-answer pairs. It knows about question 1 to n-1. But actually, the model knew a lot more about this prior question-answer history. So to be able to answer the first question, the model was doing a rich reasoning. So that's a graphical representation of baseline model that I'm going to talk a little bit in detail in upcoming slides. But basically, this kind of rich hidden states that was used to answer the prior question, can we make them available to answer the second question, basically? So that's the a basic motivation of this new model. And the baseline model, this is actually work from my friend at UW, where they are trying to build the question answering for single turn question answering task. And what it's doing is you have a sequence of query and a document, and you encode each word into word representation and contextualize them by recurrent neural network. And after this, you build this kind of query representation and document representation, you align the query to the documents and compresses the query representation into a single vector, and then concatenate into the document vectors. So why do you do that? Because the answer space is a document, so you're trying to basically select which part of the document. So basically, this way, you don't have to think about the query representation is infused into the document representation. Now there are more like RNN layers that passes the information, and on the top, basically, there is a classifier which selects where is the start span of the answer and where is the end position of the answer. So this is like a basic architecture, and there are a lot of like models, but most of them have like kind of similar architecture. And where the real reasoning and heavy lifting of finding the answer is like actually in this RNN layers. And the model is doing this RNN layers across the document tokens for question 1 and question 2 and question 3 and so on and so forth. And what we're trying to do here in this new model is creating information flow not in the same documents, but also across this other dimension of prior question to the current question. And how are we doing it? It's like basically creating another RNN layer that goes through this kind of hidden states. For same word in the documents, it has kind of sequence of chain that goes through same word, and this goes for all words in the documents. The equation is pretty complicated, but the intuition is pretty simple here. Okay. And then now we see the results by doing this kind of infusion of dialogue, history, and rich contextualized information. The model is now doing much better than the baseline model, which was pretty satisfactory, but there's still a lot of room for improvements for this data set. So in this part, I talked about how can you build like a large-scale multi-turn document QA data sets, and how can you build a better model for this particular data. And that kind of wraps up most of the main parts of the talk. But before talking about the future direction that I'm excited to pursue, I want to kind of put the work that I just described into a little bit of a context. So this 4 work became 4 separate publications when I was throughout my PhD, and I think they kind of belong to somewhat different buckets. So the entity typing work that I talked about, finding the finer grained information about entities, are kind of trying to build an intermediate representation for the models to do a higher level reasoning later. So it's not an end task in itself, because you don't really care about like, types of the entities, but these are important for it to be able to do further reasoning later on the line. On the other side, this line of work was like a more directly applicable applications. So half of them was on question answering. It's like immediate applications, and some were on like trying to find more about insights about the text, like learning about metaphors or fact checking and so forth. Yeah, so that's one categorization that I can do. Putting on the other lens, like about half of my work and like a lot of recent work is just focusing on deep neural network, where we are trying to do end-to learning with the raw text. But earlier in my PhD, I also worked on a little bit about somewhat structured knowledge base, trying to work with large-scale databases and so forth. And as I introduced earlier, some of work focuses more on building a better models, and some of work focuses more on building a better data sets. So that kind of like summarizes the overview. And lastly, I want to talk about the future directions that I'm excited to pursue. So I'm motivated with starting that like we want to really understand the entities in the text better. And like currently we are doing okay, but there are some areas that we are crucially not very good at. So one thing is the scalability. Like all the work that I introduced today talked about a sentence or like at max a longer documents. But as a human, we could kind of read the lengthy books and understand what's going on there. So actually, like bringing the model to be able to do this corpus level understanding of text is like one important direction that I would like to pursue in the future. And I have done some work. So actually, this is with Chen Hao here. It's the most recent paper where we're trying to look into analyze the relationship between 2 entities throughout 30-month periods of news articles. And like this is on US and China, and you see that after Trump made a phone call, like the announced relation kind of spiked up. So kind of getting the insight from the large scale data. And I also worked on some building a better data which include a larger scale context, and also building a model which has this kind of a hierarchical structure, which can scale better than non-hierarchical models. But there's still a lot to be done. Like, we want to understand like the trade-off between efficiency and accuracy, and how can you distill information that's in this like a really deep neural network that doesn't fit a longer text. How can you distill the information from there? It's also important future work direction. The other area that I want to talk a little bit about is like inference across different information sources. So throughout this talk, I only talked about the extracting information from raw text. But we can also work with the large-scale knowledge bases, which we have already populated the answers to. So I think that was my first publication when I was starting my PhD. We're trying to understand the queries that we could kind of map to the database to get the answer. Like, how many people have won the Nobel Prize, won the Nobel Peace Prize. And you basically go to the database and count the number of people with listed the word Nobel Peace Prize to get an answer. And there were some pros, cons, on these two different approaches. Like, one nice thing about this knowledge base is that you could do some count or mean or max operations that we actually don't know how to do that well with the raw text. But on the other hand, text contains a lot more rich and soft information. And this is not only sources of information that humans have access to. There are social media data, which is like Instagram or tweets or like Facebook. And there are a lot of information there we would like to exploit as well. And on the other side, there's like a non-language data, such as like images and videos and songs. And if you're trying to really understand entities, say Beyonce, like, just looking at the news document would be ridiculous. You should be looking at how social media talks about her, as well as the images and like videos of her. So basically, trying to understand entities better by merging these different sources of information, and how can you do it in a more interpretable fashion would be another direction that I would be excited to pursue. So lastly, I want to talk a little bit about going beyond what's written there. So this was a very first publication, also with Chen Hao here, where we are looking at the genetically modified organisms. And then on one side of the arguments, people were saying it's a green revolution, it's really amazing. On the other side, they were saying it's a Frankenfood. And you could see that there are like a very deliberate word choice that's being done here because people have different motives. And more recently, we've been looking into like politicians' statements and trying to find whether it's either factual or more likely to be false. And we did some style analysis, and we were trying to classify this automatically. We were able to do better than random, but it's a really hard problem and wasn't able to do like a, very reliable labeling. So there are a lot of room for like NLP to help understanding this kind of fact checking as well. So overall, there are a lot of things going on because humans are using language, there are intentions and motivations. So like, how can you understand text better by looking into what's going behind it, like how are we people choosing the words, and like how do that differently shape the responses. So these are also interesting directions that I would like to pursue further in the future. Okay. So I think that wraps up most of the things that I have prepared. I have this last slides that shows off the collaborators that I had for this project that I introduced today. And I'm ready for some question and answer session.
Time for questions. Any questions from the audience? Yeah.
So we call an F1 score metrics. Are they like word by word, or is it can it account also like different phrases but have the same meaning?
It cannot have different phrases that have the same meaning, but because the answer space is limited to the original document, so in the same document, usually there are not many phrases that have the same meaning.
Okay.
So, yeah. Other questions?
So the deep learning architectures presumably internally are learning all these elaborate representations of hopefully the concepts in the text. And and I think you mentioned this near the end, have you thought about, in future directions, how we might pull that out? So are they learning, and in particular, are they just learning arbitrary facts that are useful for the task that they're being trained upon? Or are they really learning the kind of concepts that we hope they're learning?
Yeah, so what they are learning is the correlation between input and output. And they're really good at it. And all the thing that I talked about is supervised system. You feed in a large scale data, there are like patterns from input to output and it captures it. But it doesn't really have like, so if you change the question, so say that you ask a question like when was Barack Obama born, it could pick out 1961. But if you ask him like, you know, how old is Barack Obama, it shouldn't be able to answer, give you the number of, so it doesn't really have the understanding in a sense that we want it to have. And I think it's a really important future direction. I really want it to be really capturing the phenomena, but in interpretability I do care, but unfortunately I don't have a very clear agenda. How can we achieve that yet?
So when you were talking about getting the fine-grained entity types and then the ultra-fine-grained entity types, I was wondering, maybe this is something you looked at already, if you had semantic or labeling for lots of data, and then you had not just the prop bank arg 0, but also the
Labels, yeah.
or the frame elements or something, if that could help you learn these more fine-grained types. Is that something that you considered? Or?
Yeah, we actually didn't consider, but there were definitely examples that when we were looking at the examples, oh my God, this is more like SRL kind of formalisms. But actually I can show some of the examples were beyond definitely SRL. So yeah, so it's like a combination of both, but for portion that, yeah, definitely SRL can help.
Yeah, give a speech. I mean, anybody can give a speech. That's not going to help you very much. But
Yeah.
arrest, if you were looking for an implicit agent of arrest,
Yeah.
then, you know, there are certain policemen are more likely.
Yeah,
to be
exactly.
arresters and things like that,
Yeah.
I'll ask a high-level question. Like you mentioned this data, the race between data model or cat and mouse. Like, do you think this will just go for the next 10 years, or how would you? I guess, yeah, I'm taking the place. Well, I want to bring that race, but you could also take the other position. But I'm just thinking about what do you think of the race in general?
Yeah, so I think there are definitely limitations on relying on like, you know, larger and larger data, just pay more and more money on the Mechanical Turk. But I think it's like really efficient for now. But I think in the future, we should be able to do more interactive learning that's not just using statically labeled data that we can only do for something that Mechanical Turker can do. So, but currently, I think it's a pretty good way to go.
Is there a better way to have some memory that can store more information rather than like RNNs and stuff?
So people have been working on different directions like memory network or embeddings that's getting updated as state goes by. But usually because we rely so much on the like Mechanical Turk style data, like there are not that many benchmarks which actually requires reasoning over like a longer text. So in a sense, data is limiting the development of the model on that side.
Oh, without further question, let's thank our speaker.